Einstein felt that there was something missing in his special theory of relativity. It was gravity. In his general theory of relativity, he proposed that gravity is not a force, but a consequence of bends in space and time.
I'm sure you've seen a picture like this, or maybe you've heard of bends in the fabric of space and time. But what is this fabric of space and time, and how can it bend?
You must be familiar with the three dimensions of space, the three dimensions of our reality. But there's a fourth dimension, it is time.
This is what the fabric of space-time looks like. Does this mean that one axis is of space and the other of time? No. Both dimensions are of space. We can have the third dimension as well, but for the sake of simplicity, we'll be dealing with only two dimensions. So how do we visualize time as a dimension? Imagine that every single element of space has a clock stitched to it. All these clocks are synchronized, that is, each of them will show the same time. And there you have it, the fabric of space and time. To understand bend in space, let's think of the path of light, which essentially travels in a straight line. Think of this ball as a photon, this pipe as space, and this magnet as a very heavy mass. Even though this magnet isn't attracting the ball, it is bending its path because it is distorting the space in which the ball is constrained to move. Similarly, the path of light is bent not because gravity is attracting light, but because it is deforming the space in which light travels.
But what does bend in time mean? Bend in time means the desynchronization of clocks in the vicinity of a bend in space.
In simple words, these clocks slow down in comparison to these. Moving on, one of the most fascinating phenomena that the general theory of relativity predicted is the existence of gravitational waves.
What are gravitational waves?
Gravitational waves are like ripples in the fabric of space-time, kind of like ripples in water. These are created when two black holes or stars orbiting each other collide and release a lot of energy. These were detected by giant interferometers at LIGO. This is how it works. A light beam is split into two light beams using a beam splitter, which reflects them along two perpendicular arms. Each of these beams is reflected at the end of each arm back to the beam splitter, where they merge into one beam. They form an interference pattern. Gravitational waves are like sound waves that travel with compressions and rarefactions. So due to a compression, one arm compresses while the other arm extends, like it happens on the balloon. The light travels a longer distance in the stretched arm. Thus, a new interference pattern is created.
Why can't we feel or see the effect? First, because everything, including the Earth, right down to the atoms, compresses. Second, the difference in length created is so small that we can't see it.
Think of it in this way. If each arm were as big as the solar system, the difference in length created would still have been shorter than half the width of your hair.